Now that we've seen how light works, it's time to look at the instruments we use to understand it. This chapter is about astronomical telescopes and the detectors we use with them to study objects in the sky. We'll start out discussing what telescopes are and some of the basic types of telescopes. Then we'll look at the properties used to describe telescopes and how they're used, and talk about how each of these affects how we observe the sky and how they define what we can see. Finally, we'll look at some special classes of telescopes that don't rely on observing the light from distant objects, but instead depend on getting information other ways. In essence, a telescope is a device that gathers light from a large area and focuses it down to a small area. The reason for needing this is simply the limitation of the human eye. All of the light we see has to come through a small hole called a pupil. This pupil is no more than a few millimeters across. However, objects in space are often very faint and have a small angular size. In other words, they don't take up much of the sky. If we're going to see these small, faint objects, we need to get more light into our eyes than what simply falls onto our pupil when we look up. The way a telescope gathers light from a large area is by using a curved lens or mirror. We're looking here at the 8-meter diameter mirror of the Gemini North Observatory in Hawaii. All of the light that falls on the large mirror or lens is bent towards a point. By putting our eye or some other detector at this point, we can have all of this light focused into our eyes. Of course, we often put other lenses or mirrors into the path to change the direction the light is going. That's what this eyepiece does. But the light gathering is the key to how telescopes work. Because of this, the most important number for describing a telescope is usually the diameter of the primary mirror or lens. We'll talk more about this number, the aperture, in a few slides. Detectors are instruments we add to a telescope to make a record of the light coming through it. Of course, the original detectors were human eyes. If an astronomer wanted to make a record of what they saw, they would simply draw a picture of it. Nowadays, there's a wide range of different detectors used in astronomy, including ones that take images like digital cameras, as well as ones that record spectra, and even some that do both. One of the most fundamental divisions in telescopes comes from what we use to gather the light, a lens or a mirror. I'd like to look at some of the key differences here. A telescope that relies on a lens to gather light is called a refracting telescope. These were the original astronomical telescopes, and they still fit many people's idea of what a telescope should look like. The classic spyglass type of telescope is a refractor. In this diagram, you can see how the light entering on the left is focused down to a point at the eyepiece on the right. However, there are certain weaknesses to refracting telescopes that make them much less popular among professional astronomers. First off, it's difficult to make a large, high-quality lens. Any imperfection within the glass affects the way the light passes through it. Also, a large lens is difficult to support. You can't put much support structure in the path of the light, so a lens has to be supported from its edges. This means that a large lens tends to sag under its own weight. Lenses are also subject to something called chromatic aberration. We've already seen that when a piece of glass bends light, it bends different colors by different amounts. This is how a prism is able to split white light up into a rainbow. However, the glass of a lens does the same thing, causing different colors to focus onto different points. When you look at an image, you see colored fringes along the edges of objects because only one color is in focus at a time. Chromatic aberration can be corrected using 2 or more kinds of glass at once, but this makes the lens more complex to make and causes it to lose more light. The problem is less if the lenses aren't very curved, but then you need a telescope that is extremely long. The last problem is that lenses only work for visible light. The glass of the lens blocks other kinds of light, so it can't be used for observing outside of the visible spectrum. The largest refracting telescope was built over a century ago. It's the 1-meter Yerkes telescope in Wisconsin. In this picture, the primary lens is at the far end of that long tube. Telescopes that rely on mirrors to gather light are called reflecting telescopes. Reflectors now completely dominate astronomical observing. Have a look at the diagram on the right. It shows the light entering the telescope from the right side, then hitting the primary mirror on the opposite side of the telescope. From here, the light bounces back up the telescope tube, after which several things can be done with it. In this example, a small mirror reflects the light over to the side of the telescope. Reflecting telescopes are much easier to build than lenses. You can have a large superstructure to support the mirror without blocking the light. Look at the steel casing on the bottom of this large telescope to hold the primary mirror. Also, only the surface has to be smooth, not the interior of the glass. This is the underside of that same telescope. Look at all the little bubbles embedded in the greenish glass here. If the light had to go through all of that like a lens, it would be scattered all over. But since the light only bounces off the top surface, these bubbles don't matter. Mirrors don't suffer from chromatic aberration. All wavelengths are reflected the same way. Also, they can be used for any kind of light, not just visible light. These radio telescopes are also just big mirrors. The largest optical telescopes have a diameter of about 10 meters, 10 times the size of the largest refractors. There are several that are close to the same size, including this one in the Canary Islands. The largest radio astronomy dish is 30 times the diameter of the largest optical telescope. The largest mirrors are now built in many segments and then combined. The 10-meter Keck of telescopes in Hawaii are a good example of this. Notice that each segment is about a meter across, or more than half the height of the person sitting in the center.